Alright, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So today we're going to continue on chi-squared test. This is a part B where we're going to continue from the previous lesson. We already look at how to do a goodness of fit test from example number 1 until example number 4. So today we're going to continue on the same topic, but different area. We want to see in other application, right? So now a goodness of fit test. It is possible to design a goodness of fit test to determine whether data are consistent with the data drawn from a particular probability distribution, for example binomial distribution, Poisson distribution, and others type of distribution. So the state of hypothesis is, null hypothesis is, the data follow either binomial distribution or Poisson distribution. Alternative hypothesis, the data does not follow either Poisson distribution or binomial distribution, right? So second step is we need to find the probability value using the formula from the dead distribution. For example, if you are using Poisson distribution, so the probability of x should be equal to exponential of negative lambda multiplied with lambda power of x divided by x factorial. And same goes to binomial. If you are testing for a binomial distribution, so the probability of x should be equal to n choose x multiplied with probability of success power of x, and then q, or 1 minus p, is multiply power of n minus x. And then step number 3 is we need to find the expected value. So the expected value are the formula same as before, which is expected value is equal to n multiplied with p. So the expected frequency should be at least 5. When the expected frequency of a class category is less than 5, so this class or category can be combined with another class or category so that the expected frequency be at least 5. So this is the condition that we already agreed from the previous class. When the expected frequency is less than 5, we cannot proceed with the Pearson chi-squared test. Sorry, we cannot proceed with the Pearson chi-squared test. If the expected frequency is more than 5, then we can proceed with the Pearson chi-squared test. So then step number 4 is we need to find the test value, which is the Pearson chi-squared statistics. So the Pearson chi-squared statistic is equal to the summation of observed frequency minus expected frequency. This is squared, right? Divide by the expected frequency. So the summation of this value, so you will get the Pearson chi-squared statistics, right? Step number 5. We need to find a critical value, right? This is a bit different from the first one. Find the critical value that the right tail of the chi-squared distribution. For example, the degree of freedom for the critical value is k minus 1, where k is the number of frequencies and the number of restriction total agree should be equal to 1, right? So that's why we minus with 1. So the degree of freedom described here should not be used unless each of the expected frequency is at least or equal to 5. This is the most important condition that we need to check. So this restriction may require the combination of adjacent cell resulting in the reduction in the number of degree of freedom, right? So then step number 7, we need to do a decision, right? We're going to reject null hypothesis if the chi-squared calculated more than chi-squared alpha with degree of freedom, and then we make a conclusion on step number 8, right? Right, on example number 5, let's look at example number 5. So first, in example number 5, we are showing about a binomial distribution, right? So let's look at the question in example number 5. 4 coins are thrown 160 times, and the distribution of number of head is observed. So this is our random sample, right? And observe, this is from the result is in table number 2. This is table number 2. So our question is there any evidence that the coin are biased, right? So we need to test at alpha 0.05. So we have basically number of head 0, 1, 2, 3 and 4. So we have 4 possible outcome, right? So the frequency of number of head is 0 is 5. Number of head equal to 1, 30, 35, 67, 41 and 12. This is frequency of number of head. So now step number 1, we need to state our hypothesis. So the null hypothesis is the data follow binomial distribution with the probability of success is 1/2 and equal to 4 when the coin is unbiased lah. We toss a coin, right? If the alternative hypothesis, so but before we go there, right, if you can see the probability of success is 1/2 is because if you toss a coin, either you getting head or tail. So the probability of getting head is 1/2. Probability of getting tail is also 1/2. So that's why the probability equal to 4, right? So now alternative hypothesis, data does not follow binomial distribution with p equal to 1/4 and equal to 4, right? Right. So step number 2, we need to find the probability value using the formula n choose x. Probability of success power of x 1 minus p and power of n minus x, right? So if you're wondering why n equal to 4, you need to carefully read the question, because we have 4 coins are thrown 160 times, right? So now we need to create a table consists of number of head. This is a sample space, right? Our sample space, and this is the frequency, which is observed frequency, and this is the probability of success. The value of probability, right, we will get from the formula of binomial distribution, right? So for this example, let's say the first probability value, so we will get 4 choose 0, so n is equal to 4 choose 0, right? Multiply with the probability of success is 1/2 power of 0, multiply with the complement of probability of success is 1/2, multiply with 4 minus 0. So this one should be equal to, if you key in into your calculator, 4 choose 0, right, is equal to 1, multiply with 0.5 power of 0, right, and then multiply with 0.5 power of 4, right? You should get 0.062, so 0.0625. So this is also equal to 1/16. Sorry, 1/16, right? So this is 1/16 lah. So same goes to the second row of the probability. right? You can calculate by using the same formula, using the binomial distribution. 4 choose 1, right? 1 over 2 power of 1, and then multiply with 1 over 2 power of 3. So you will get 4 over 16, right? And so on. So the expected frequency is based on n multiply with probability of success. So this is the expected frequency. So the expected frequency n is equal to 160 multiply with the probability value 1 over 16, you will get 10. So by looking at the first table, you should check for each the value of expected frequency. If is there any expected frequency less than 5. So based on our calculation, there are no expected frequency less than 5. So we can proceed with the calculation. So we have our observed frequency and expected frequency. So observed minus expected frequency. So this is the modulus, right? So we disregard the negative sign because at the end we're going to square the value. So the value of observed minus expected should be positive, always positive. So this is 5. So 5 minus 10, it should be equal to negative 5, right? So we're taking a modulus, so it should be 5 and so on. And we take a square of the observed minus expected, and then we calculate the goodness of fit value, which is observed minus expected square divided by expected, right? So 25 divided by 10 should be equal to 2.5, right? So then after that we need to calculate the total of all goodness of fit value to get the chi-squared calculated, right? Should be equal to 4.367, right? So then this is the step number 4 is the Pearson chi-squared statistics. So this is the value of Pearson chi-squared statistics, which is 4.367. Right, now step number 5, we have basically 5 classes. This is class number 1, class number 2, 3, 4, and 5. Right, we have 5 classes. So this is our K, right? Now the number of restriction is equal to 2 because we are calculating the probability value using the formula, right? Using the probability formula, right? If you apply any distribution formula into our statistical table, we need to extra minus extra 1, right? It should be degree of freedom should be equal to k minus 1 minus 1. So this is the normal calculation degree of freedom, right? So this is we minus 1 because we are using the formula. We are using the formula to calculate the degree of freedom, right? So we reserve another agreement, right? So that's why the degree of freedom is equal to 5 minus 2 equal to 3. So the critical value should be a chi-squared with 3 degree of freedom and alpha 0.05. So this one should be equal to 7.815 if you round up. So the decision, if the chi-squared calculated is more than chi-squared critical value, so this is, let's draw the critical region, right? So this is a distribution curve. Let's say this is 0.05, which is our alpha, and this is a chi-squared 3 0.05, which is 7.815. As you know, on the right area the area on the right is rejection region, and the area on the left is acceptance region, right? So if our chi-squared calculated lies on the rejection region, so we will reject the null hypothesis. If our chi-squared calculated lies on the acceptance region, so we will accept null hypothesis. So since our chi-squared calculated is equal to 4.367, somewhere here, 4.367, so less than our critical value, right, is lies under acceptance region, so we will accept null hypothesis. So we will accept null hypothesis, or in other words, we fail to reject the null hypothesis. So our conclusion is we do not reject null hypothesis and conclude that there is no evidence that the coin are biased, right? So that's how we answer this question lah. Right? So now let's look at example number 6. In example number 6, alright, on example number 6, there are 1000 bags of orange, right? 1000 bags of orange. Each contain 10 orange. Each bag contain 10 orange. Some of orange are rotten, right? Is the distribution of rotten orange in the individual bag is a binomial distribution. Binomial with n equal to 10, p equal to p lah. And let alpha is equal to 0.05. So this is the number, the frequency value, the frequency table. We have the number of rotten orange per 10 bags, right? For 1000 bags. So 0 rotten is 334, 1 is 369 until 6 rotten orange. So now we wish to test that whether the distribution of rotten orange in individual bags is a binomial distribution with n equal to 10 and p is equal to p, right? So we will calculate p individually. So our hypothesis statement is a null hypothesis equal to the count of rotten orange follow a binomial distribution, where the alternative hypothesis, the counts of rotten orange does not follow a binomial distribution, right, where alpha is equal to 0.05. So from here we know that our n is equal to 10 and p is remain unknown, because we need to calculate the value of probability of rotten, right? Then we need to do a second step, which is test statistic. So in our test statistic, we really don't know the value of p, so we need to estimate the value of p using the probability value lah, right? Right, so this one we need to do a test statistics. So as usual, we're going to create a table, right? Like I'm drawing the table first. So we're going to have a rotten orange, right? And then we're going to have our observed frequency, which is f, and then we need to calculate the probability of success, which is probability of rotten, and we're going to calculate expected value or expected frequency, and then we're going to calculate observed minus expected frequency, observed minus expected frequency square, right? And then the last one is our goodness of fit, which is observed frequency minus expected frequency square divided by expected frequency, right? So this is the value that we're going to calculate. Let me draw the line first. So the first class is about 0 rotten, 1, 2, 3, 4, 5, and 6. And the last one we have total, right? So let me create the line first, right? Right, so we just need to input our value of frequency. The first value of frequency, 0 rotten, is 334. This is 369, 191, 63, and this is 22, 12, and 9. The total should be equal to 1000. So next step is, since we are measuring whether the counts of rotten orange follow a binomial distribution, so probability of binomial distribution is n choose x, probability of success power of x, and 1 minus p power of n minus x, right? So we know from here is right, so each bag contain of 10 orange, right? So we're going to measure for individual bags, right? So this one, let's say for the first one, and 10 choose 0 power of probability of success. So now in here we don't really know the probability of success, right? So that is our main problem. So now to find the probability of success here is we can use another method. We try to extrapolate the value of p. Let's say we're going to use expected of x. So expected of x is also equal to np. So this is based on the binomial distribution where np is equal to x bar, our mean of random variable x. So if you can do a manipulation here, so x bar divided by n is also equal to p hat. So this is our probability of success. So we want to estimate the probability of success. So now based on the formula, probability of success is equal to x bar divided by n. If we convert it to, if you try to match it with our frequency table, right? In frequency table, mean is equal to summation of fx divided by summation of f. So this one should be equal to summation of fx divided by summation of f. So this value is equal to x bar, right? And then divide by the value of n, right? So we know that our n is equal to 10, right? So now summation of fx, right? This is x, this is fx. We just need to key in into our calculator. Let's say I'm using let's say shift mode. No, I'm not going to use this one. Right, say shift mode. So first we need to click on shift and make sure the shift icon here, and we click on the mode button, and then we try to find statistic, right? Number 4, right? So we need to on the frequency value, right? So now we're going to choose mode one time and click on 3 for statistic, and we're going to use 1, right? So here is the value of x, and this is the value of frequency. We just need to key in the value carefully, right? 2, 3, 4, 5, 6, right? And then this one should be 334, and this is 369, this is 191, right? This is 63, 22, 12, and 9, right? So we can recheck our data imputation in our calculator and click on AC. So then we click on shift 1, and we try to find 4 and sum number 3, and click on number 2, summation of x, which is equal to summation of fx. So from here we know that summation of fx is equal to 1142, right? And then if you want to find the summation of x, summation of f should be equal to, this is a total, right? So we know that summation of f is equal to 1000, right? So summation of f is equal to 1000. So now we can input the value into the formula. So 1142 divided by 1000 divided by 10. So this one should lead us to 0.1142, right? So this is our probability of success. So now, since we already get the value of probability of success, we just input into our formula. So the probability of success is 0.1142 power of 0, right? And then 1 minus 0.1142 should, this is 1 minus 0.1142 should be 0.8858, 0.8858. So power of 10. So this one should be equal to, so if you input into a calculator, let's say click on this one. So 10 choose 0 is equal to 1, multiply with the value of probability of success, 0.1142 power of 0, right? And then multiply with this is going to be 0, right? 1, 0.8858 power of 10. Oops. So this one should be equal to 0.297, right? So the probability of success, probability value here is 0.297, 2974. Is it? Yeah, 2974. Right, so you need to calculate the value of probability for each rotten orange. So this one should be 0.3834. This is 0.2224. This is 0.0765. And this is 0.0173. This is 0.0027. And last is 0.003. The total should be equal to 1. Right, so since we already calculate the value of P, now we should calculate the value of expected frequency. So the expected frequency is equal to n multiplied with probability of each category. So 1000 multiplied with 0.2974. So this one should be 297.4. This is 383.4. This is 222.4. This is 76.5. This is 17.3. This is 2.7. This is 0.3. Right. So if you look at the expected frequency here, there are two rows having expected frequency less than 5. So this is expected frequency less than 5, right? So this is very small expected frequency, right? So we need to combine these two rows until we get expected frequency more than or equal to 5, right? So what we need to do is we're going to combine these two rows together. Even we combine these two rows together, right, we still get the expected frequency not more than 5, right, which is still less than 5, which is equal to 3.0. My advice is we need to combine this row and this row together, so we can get the expected frequency more than 5. So now let me do this one. Let me copy this table again, right, so we can see the difference between, right. Right. So I just copy the same table. Now what I want to do is I'm going to combine these two table, these two row with table row number 5, right? So this is going to be 4 and above lah, right? 4 or more, right? So this one should be the total from 22 plus 12 plus 9. So this one should be 22 plus 12 plus 9. So this one should be equal to 43, right? So I just rub this one, 43, and this one should be nothing lah. So I'm going to combine the probability value here, right? No, I'm not going to combine the probability value. It still remains same. So I'm just going to combine the value of expected frequency, which is equal to 17.3 plus 2.7 plus 0.3. So we're going to get 20.3. So this one should be 20.3. 20.3. Right? We already combined this expected frequency from from row number 4 and 5. So now we can calculate the value of observed minus expected frequency, right? So now observed minus expected frequency, 334 minus 297 should be 36.6. This is negative 14.4, negative 45.8, and this is negative 13.5 for this one. Right, 43 minus 20.3, right, should be equal to 22.7. Right, now square this one should be 1339.56. This is 207.36. 2097.64. This is 182.25. This is 22. Sorry, we need to calculate this one. 22.7 square. Oops, 22.7 square. So it should be 515.29. 515.29. Right. Right, then we need to calculate the value of goodness of fit. So this one should be, let me use another color. Right, this is 4.5042. This is 0.54085. This is 9.4318. This is 2.3824. And then for this one, 515.29 divide by 20.3. So this one should be 25.3837. Right. So the total of goodness of fit value 4.504. Oops. This is 4.5042 plus 0.54085 plus 9.4318 plus 2.3824 plus 25.3837. So this one should be 42.24. 42.24. Right. So now the next step is, we know that chi-squared calculated is equal to 42.24, and the critical region is, let's say, let me draw the distribution curve. So this one is our alpha 0.05. This is our chi-squared calculated. Let's say k is equal to how much? K is equal to now our k here, we after we combine the category, we have 1, 2, 3, 4 and 5. So our k is equal to 5, right? So our degree of freedom is 5 minus 1 minus 1, so it should be equal to 3. So our chi-squared critical region degree of freedom is equal to 3, 0.05. Our alpha is 7. How much from the previous example? 8.115. 7.815. So this is 3, 0.05 is equal to 7.815. So the next step, we need to make our decision. Our decision if a chi-squared calculated is more than a chi-squared 3, 0.05, null hypothesis is rejected. So since a chi-squared calculated is equal to 42.24, which is somewhere here, right? So which is more than a chi-squared 3, 0.05, null hypothesis is rejected, right? So our conclusion is the data does not follow binomial distribution, right? So the data does not follow binomial distribution. So our hypothesis is the null hypothesis data follow binomial distribution. Alternative hypothesis, the data does not follow binomial distribution, right? So that's how we solve the problem, right? So now let's look at example number 7, right? So in example number 7, so it's the same procedure, right? So we have 4 identical 6-sided dice, each of with face 1 mark 1 to 6 are rolled 200 times. Each rolling, a record is made of the number of dice whose score of the uppermost face is even. The result are as follows. So we have a 200 roll of die, right? So explain why a binomial distribution binomial model might be described the distribution of x and test the goodness of fit test. So this step is also same as example number 6, right? So I think I'm not going to touch in example number 7 because I'm going to repeat the same procedure, right? As this go to same as example number 8, right? Example number 8 and example number 9, but example number 9 is quite different, so I'm going to touch on example number 9. So far what I want you to do is I want you to treat example number 7 and example number 8 as your homework. So try to solve the problem, try to test whether the data can serve as a binomial distribution or not, right? I think that's all for example number 7 and 8, right? So now look at example number 9. Alright, example number 9. This example we will show another procedure, which is by using a Poisson distribution, right? So the following table number 3, this is table number 3, give a record of number of radio message received by air traffic control during 405 minutes interval, right? So test at alpha 0.01 whether the data can be looked upon as value of a random variable having a Poisson distribution with mean equal to 4.6. So this is our mean 4.6 for Poisson distribution. So we want to test whether this data follow a Poisson distribution. So by looking at the frequency table, we have a number of radio message 0 until more than 8. So this is the frequency value. So the steps are same as previous example. So first step, we need to state our hypothesis statement. So our null hypothesis statement is the data follows Poisson distribution with mean equal to 4.6. And alternative hypothesis, the data does not follow Poisson distribution, right? So this is the Poisson distribution formula: exponential negative lambda lambda power of x divided by x factorial. So step number 2, right, we need to find a probability value by using the formula mean equal to mu. So we are going to use this formula basically, right, to find the probability value. And as usual, we're going to create a table. So this is our number of class, which is number of radio message, 0 until more than 8. And this is observed frequency. And then the next column is our probability value. So the probability value is get from the formula px equal to exponential negative lambda power of x over x factorial. So this one, if you look at when x equal to 0, exponential negative, our lambda is 4.6, right? Our lambda is 4.6, lambda 4.6 power of 0 divide by 0 factorial. So you will get 0.001. So the next row also using the same procedure, right? And then for column number 4, which is expected frequency, right, is get from n multiplied with pi. So n is equal to 400 multiplied with 0.01, which is equal to 4.0, right, and so on. So next step is we need to calculate, we need to find the value of goodness of fit value, and then add all the value of goodness of fit to get the chi-squared value. So this is a chi-squared calculated, right? So basically it's just the same procedure, and then we just need to change the formula from a binomial distribution to Poisson distribution to find the probability value, right? And then step number 4, still same procedure. We need to find the critical value, right? Critical value, we have k is equal to 8, right, minus 1, and we need to minus another 1 because we are using formula. We are using formula to calculate probability, using formula to calculate probability, right? So that's why 8 minus 2. So we will get the degree of freedom. This is a degree of freedom. The degree of freedom should be equal to 6. So we're going to find the value of chi-squared alpha 0.01 and degree of freedom equal to 6, which is equal to 16.812. And then the next step is we need to make a decision, where our decision is when the chi-squared calculated more than chi-squared the critical region, then we're going to reject null hypothesis. So since our chi-squared calculated is equal to 6.3466, so which is less than 16.812, which is our critical value, so we will accept null hypothesis, or in other words, we fail to reject null hypothesis. And then we can conclude our decision, which is we do not reject null hypothesis, and conclude that the Poisson distribution with mean equal to 4.6 is provide a good fit, right? So that's how we solve the problem, right? So now, by looking at that step, let's look at example number 10. So in example number 10, right, it's the same procedure. The number of computer malfunction per day, is recorded for 260 days with the following result. So number of malfunction from 0 until 5, right? This is our frequency, observed frequency, and the total for observed frequency should be equal to 260, right? So we observe 260 days. So same step, first step, we need to state our hypothesis statement. Our hypothesis statement, null hypothesis, the number of malfunction, number of daily malfunction daily malfunction is follow Poisson distribution with mean equal to lambda is equal to what is the value of lambda? We do at this stage we really don't know the value of lambda, and we need to calculate the value of lambda later. So now alternative hypothesis, number of daily malfunction does not follow Poisson distribution, right? So our alpha is equal to, let's assume alpha is equal to 0.05, right? Because it does not state any alpha value, so we just assume 0.05. So now our problem now, before we start with the calculation test statistics, we do not know the value of lambda. So to find lambda is actually expected value, right? The expected value of x is our lambda, and also the value of variance of x is also lambda if the distribution is a Poisson distribution. So this one by definition is summation of fx over summation of f. So this is our mean, right? So we need to calculate manually. So by using your calculator, again the same step. So we need to clear our memory, right? Let me click on shift 9 all. Yes, so we clear all the memory. So click on shift mode, and we need to find statistics number 4, and we need to on our frequency value, right? And then click on mode, click on 3 for statistics and 1 for 1 minus variance. So we input our x value, right? So we don't have any 6, we until 5, right? So we input our frequency value 77, 90, 55, 30, 5 and 3, right? So we want to find the value of fx. So shift 1, click on 3 and click on 2 for summation of fx. So this is 325 divided by 260. So this one should be equal to 1.25, right? So now let's we already know lambda is equal to 1.25. So lambda is actually equal to mean. If the mean, if this form distribution data followed Poisson distribution, so the mean value should equal to variance value, right? So if you are not sure, you can calculate the value of variance. So now the next step is we need to find test statistics. So test statistics, right? So as usual, we should have a table. Let me create a table first, right? Right, so in the table we should have x value and observed frequency, and then we need to calculate the probability value, expected frequency, observed minus expected frequency, and then observed minus expected frequency square divided by expected frequency, right? So x value we have from 0, 1, 2, 3, 4, 5, and the last is total, right? So the value of observed frequency is 77, and then this is 90, 55, 30, 5, and 3, and the last total should be equal to, sorry, we have more than, do we have more than 6? So we don't have value of more than 6, right? And then this one should be equal to 260, right? Now let's try to do this one first, right? Let's see what going to happen. So now let me create the line. Oops. Right, so now to calculate the value of probability, right, we already know the value of lambda is equal to 1.25, right? So probability of x equal to 0 is exponential negative 1.25, and then 1.25 power of x equal to 0 divided by 0 factorial. So this one should be equal to 0.2865, and this one 0.3581, 0.2238, 0.0933, this is 0.0291, and this is going to be 0.0073. And first you need to recheck whether our sum of probability, the total probability, should be equal to 1. 2865 plus 0.3581 plus 0.2238, 93 plus 0.0291 plus 0.0073. So obviously the total of the probability is not equal to 1, right? So that's why we need to add another row which is more than 6, right? 6 or more. So this one should be 6 or more. So more than, oops, this is more than 6. Obviously there are no value here, and this is going to be 1 minus answer should be 0.019, 0.0019, right? So now then the total value should be, the total value of probability should be equal to 1. This is 260. There are no value more than 6, right? So the expected frequency is equal to n multiplied with probability of each row, right? So this one 260 multiplied with 0.2865 should be 74.5, right? And this one should be 93.1, 58.2, this is 24.2, 7.6, 1.9, and this is going to be 0.5, right? So if you look at the frequency the expected frequency, so we have basically two rows having expected frequency less than 5. So basically we need to combine these three rows together, right? We need to combine these three rows together, so then the expected frequency is more than 5. So let me copy the table again. right? So let me paste here. Oops. What happened? Oh, yeah, okay. Right. Right. So now I'm going to combine these three group together. So this one should be equal to more than or equal to 4, more than or equal to 4. And this one should be 5 plus 3 equal to 8. And this one should be equal to 7.6 plus 1.9 plus 0.5. So this one should be equal to 10. Right, so I just put 10 over there. This is 10, right? So then what we need to do is we're going to calculate the value of observed frequency minus the expected value. So the first value is 77 minus 74.5. So this is going to be 2.5. And the next one is 90 minus 93.1 should be negative 3.1, right? And then 55 minus 58.2, this is negative 3.2, right? And then 30 minus 24.2 should be 5.8, and then 8 minus 10 should be negative 2, right? So this is negative 2. So now to find the value of goodness of fit, which is observed minus expected square divided by expected value. So this one should be 2.5 multiplied with 2.5 divided by 74.5. So this is 0.084. 0.084. So this is 0.103, 0.176. This is 1.39. And the last one should be 4 divided by 4 divided by 10. So this is 4 divided by 10. So this is 0.4 lah, 0.4. And the total of the observed of the goodness of fit value, it should be equal to 2.153, right? So now we already have the value of a chi-squared calculated. Chi-squared calculated should be equal to 2.153. So let us draw a critical region. Our critical region, let me draw the curve, chi-squared curve, distribution curve. So this is 0.05, our alpha, and this is a chi-squared with a degree of freedom and 0.05. Right. Now our degree of freedom is equal to k minus 1 minus 1, because k minus 1 is a fixed value, minus 1, another one is because we are calculating the probability value using the formula. So now by looking at this one, we have basically 1, 2, 3, 4, 5 class. So our k is equal to 5 minus 2, which is our degree of freedom now become 3, right? So chi squared with 3 degree of freedom with alpha 0.05 is equal to 7.815, right? So our decision rule if a chi-squared calculated is more than a chi-squared with 3 degree of freedom, alpha 0.05, null hypothesis is rejected, right? So since our chi-squared calculated equal to how much that is 2.153 is less than 7.815, null hypothesis is accepted, right? So our conclusion is the number of computer malfunction per day does follow Poisson distribution, right? So that's how we use a goodness of fit test to test whether the data is following some distribution, whether the binomial distribution or the Poisson distribution, or you can use you can twist to normal distribution, Bernoulli distribution, gamma, and so on, right? So it's the same procedure, same step, right? So I think that's all for today, right? So I just want you to understand the concept of how to test the hypothesis, goodness of fit test, to determine whether the data is following a binomial distribution, Poisson distribution, and others distribution, right? So don't forget, you have example number 7 and example number 8 to solve by yourself, right? So this is please treat this as your homework, right? I think next class we will meet on test of independence, right? Still under chi-square test, right? On the next class we will see on test of independence, right? So I think now until now, so if you have a question, please comment on the chat room below, right? And please comment if you have a question, or if you understand, please also comment, right? And I hope you understand all the method today, right? So I think that's all. Thank you very much, and Assalamualaikum.